What if everything you see is just a mask, hiding a spectrum you never knew existed?
This black dot, it's not black at all. It's a lie, told by a mixture of colors, all trapped together.
But to reveal the truth, to unmask the liar, we need a key. A simple, clear, and powerful solvent. We stand the paper in the solvent, just touching. The line of ink must stay high and dry, watching, waiting. The solvent climbs, carrying the ink with it. But they don't all travel together. They separate. Look, a single black dot has become a rainbow. We've unmasked the ink. This is a chromatogram. To understand how, we need to shrink down, way down, into the microscopic world of the paper itself. Each color is a different substance. Some are sticky, clinging tight to the paper fibers, reluctant to move. Others are slick. They love the solvent, surf its leading wave, and race ahead. It's a race to the top. The result? A separation. The fastest at the top, the slowest at the bottom. A chemical race decided by invisible forces. In the lab, we use a pencil line. Why? Because ink would dissolve and ruin the experiment. Precision is key. We roll it, place it in a chamber with solvent at the bottom, and cover it. The waiting game begins.
The solvent rises, the colors bloom and race, and soon a story is told on this paper canvas.
When the solvent nears the top, we stop. We mark the solvent front, and we see what the race has decided. But what if the culprits are invisible? What if we can't see them at all? The mystery deepens. Meet mixture Y. It's clear, like water. We suspect it contains suspects A, B, C, and D. But we need proof. We spot them on the paper, Y and our suspects. But there's nothing to see. They're ghosts. The solvent rises, doing its job. But we see nothing. The separation happens in secret, invisible to our eyes. We dry the paper. Still nothing. The evidence is there, locked inside, waiting to be unlocked. We need a magic trick, a locating agent, a chemical that will make the invisible visible. And then magic. Purple spots appear, like ghosts stepping into the light. The invisible evidence is finally revealed. We compare. The spots from Y line up perfectly with A and B. The verdict? Y contains A and B. Case closed. A single spot tells us a substance is pure. But which substance is it? We need its name, its identity. We measure. From the starting line, the origin, to the heart of the purple spot. That distance, let's call it 26 millimeters. We lock that number in our memory. Next, we measure the total distance the solvent traveled, from the origin to the solvent front, say 68 millimeters. Now, we calculate. We divide the distance the substance traveled by the distance the solvent traveled. The answer, 0.38. This is its RF value. Its chemical fingerprint. We become detectives with a database. We consult an RF table, a library of chemical fingerprints. And there it is, 0.38, a perfect match for alanine. We haven't just separated it, we have identified it by name.
This is the power of RF, a universal language, a way to name the invisible, no matter the lab, no matter the scientist.
Every spot gets a number. Every number tells a name. The chromatogram becomes a map of known identities. This isn't just for labs. Chromatography is everywhere, even in your candy. We take the purple one. We dab its color onto our paper. The mystery is it one purple or a mix?
We run the experiment. And look, that purple candy, it was made from red and blue dye. The label was hiding the truth.
Or imagine a crime scene, a single drop of blood. What secrets does it hold? We spot the sample. We run the solvent. We're not looking for color now. We're looking for evidence.
We use different locating agents. Under UV light, hidden components glow like ghosts, revealing their presence.
We compare the glowing fingerprints to a database, a match. The blood is identified, a clue is born. From crime scenes to the forest, why is a leaf green? Let's ask chromatography. We grind a leaf with solvent, extracting its green pigment. We spot it on the paper. The single green spot blossoms. Yellow appears, blue-green, yellow-green, a hidden ecosystem of pigments.
The leaf isn't just green. It's a canvas of yellow xanthophylls, blue-green chlorophylls, hidden beneath the dominant green. Chromatography revealed its truth.
We are told a substance is pure, 99.9%. Perfect. But is it? Let's put it to the test. We take a sample of this perfect X and spot it on our paper. We run the solvent. The solvent does its work. We wait. We dry. We spray our locating agent. A beautiful, strong spot appears. That's our X. But wait, look closer. There, a tiny ghost, a second spot, an impurity. The pure X has a secret. That's the power of this test. It finds the 0.1% impurity that other tests miss. No secrets can hide.
It's not about proving something is perfect. It's about finding the truth, no matter how small.
The solvent front is the finish line. RF values are always between 0 and 1. Even if the solvent travels different distances, the RF value stays constant. It's a ratio, not an absolute distance. We cover the beaker to saturate the air with solvent. This prevents the paper from drying out and ensures a clean, consistent run. Change the solvent and you change the race. RF values are only valid for a specific solvent and condition.
Today, we have machines that cost millions. They can identify a substance in seconds. But in the corner, often forgotten, sits the original detective. Paper chromatography.
Okay, I'm spotting the marker now. Whoa, look, the test is in there. Look at mine, it's all separated.
Awesome! Science is so cool!
From food safety to field forensics, from remote jungles to quality control labs, it's still there, solving problems. It's a reminder that the biggest truths are often found in the simplest tools. A piece of paper, a little solvent, and a question. Paper chromatography. It doesn't just separate colors, it reveals the hidden spectrum in everything. Keep asking why.